Let's take a look at an example for Le Chatelier's principle. So we have this equilibrium equation here, N2 plus 3H2 giving you 2NH3, which is ammonia, plus 22 kilocalories. Remember, kilocalories is a unit of energy, just like we use kilojoules. Notice because it's on the right-hand side, we would say that this is exothermic in the forward direction. And if we are to look at the reverse, it would be endothermic in the reverse direction. So let's take a look at how various stresses applied to this system at equilibrium will have an effect. So let's take a look. If we add some N2, so we increase this concentration, this will be shown as the stress here. What will happen? Well, this is saying that the system will shift to the right. So if we think about this, if we increase this here, well, what will happen is the system must counterbalance that increase, and we must use some of that up because there's too much. The only way to use up some of that N2 is for it to collide with some more H2 to form NH3. That's how it compensates for the excess in N2. So the system will shift to the right. In shifting to the right, this concentration will go up. And what will happen is these concentrations of N2 and H2 will go down. It's sort of like this teeter-totter. So we were at a balance. So we always sort of do the opposite effect. Let's take a look. If we were to add some H2 to the system, what effect would that have? So if we add some H2, we want to counterbalance that influence, and we need to use some of it up. So in order to use some of it up, we need to have it shift to the right to make more of this so that this concentration goes down. So what will happen is, again, we're going to shift to the right, and I'll just use an arrow. And what happens is if we're shifting this way, the N2 is getting consumed. So that concentration will go down and your NH3 concentration will go up. Now, what if we increase this concentration? Well, again, the system always wants to shift to do the opposite effect. So if we're adding this, the system will shift to try and decrease that concentration. So the only way to decrease that concentration is to shift towards the left. And in shifting towards the left, we will see that the N2 and the H2 concentrations will go up. Okay, so we're going to make more of those reactant molecules in order to consume some of the NH3. Now, the same thing happens when you are removing, okay? So if we end up taking some of this N2 out of the system, then what will happen is the system is like, oh no, we need to quickly make more. The only way that you can make more is by shifting the system towards the left, where we make more of this and we use this up. So the NH3 molecules will be colliding with one another to reform some of this. So what we want to do is the system will shift left to quickly make some more. And that means that your H2 concentration will go up because it's on the left, but your NH3 concentration will go down. The same effect will be felt if you happen to remove some H2. So if we remove some H2, the system says, oh no, we need to make more of it. The only way to make more is to shift again towards the left, okay? And what will happen is, as a result, more N2 will be made and your NH3 will go down. We'll get to the last column in a moment. Similarly, if we remove some NH3, that means you're decreasing that concentration of NH3. The system must shift to make more of it. So if we shift to make more, we would be shifting towards the right. Shifting towards the right brings that concentration back up. And so that means that the concentration of N2 and H2 will go down when we shift towards the right. Now, what happens if we increase temperature? So temperature is the only variable that really affects the equilibrium constant in terms of the value. All of these other influences will shift so that the ratio of reactants to products remains the same so that the value of KEQ does not change. Why does temperature effect? Well, what we will see in a moment is that we sort of treat this energy value like a reactant or a product. So if we see that energy is on the right-hand side of this equilibrium equation, what we would do is we'd say, okay, if this energy goes up, we need to reduce that energy. And the only way to reduce it is for that to be consumed. And the only way that it will get consumed is if we proceed towards the endothermic process. Okay, so we want the system to shift left if we have an increase in temperature in this particular case. If we do that, that means that your N2 and your H2 will go up and your NH3 will go down. The opposite will happen if this is being dropped, okay, just like a concentration, okay, if this is going down, we need to shift in order to bring that energy value back up. The only way to do that, in order for us to release more heat, to get more energy, we have to shift towards the exothermic process. So what we would do is we would be shifting towards the right if we decrease the temperature in this case. And when we shift towards the right, that means the concentration of N2 goes down, the concentration of H2 goes down, and the concentration of NH3 goes up. So let's take a look at what effect that would have on your KEQ value. So what I just did very quickly on the back is I rewrote out this equilibrium expression, and I wrote out the mass action expression. So we've got the products raised to their exponent, all divided by the reactants raised to their exponent. Now, let's just say that this value of concentration happens to be a 1, and this value, when we multiply these together and whatever, happens to be a 5. Okay? Now, if we increase temperature, if we increase this, what we are doing is we are shifting the reaction towards the left. So that means that we are making more reactant. So your numerator is going up in value, and this is going down in value. Whenever you have a large denominator compared to your numerator, then that means that your KEQ value is going to be much smaller. Okay? Okay, so you're going to get a smaller value. When we have the opposite happening, when you have an increase in temperature, or sorry, I should say a decrease in temperature, your system is going to shift towards the right. So when we shift towards the right, what ends up happening is you are making more of your product. So we are making more product. Your numerator goes up and your reactants go down. When you have a big number divided by a small number, your KEQ value gets much larger. Okay, so the effect on your KEQ value is affected by temperature. Okay, so again, when we increased the temperature in that particular case, we saw that our KEQ value went down, and in this particular case, our KEQ value went up. Okay, so the next scenario that we want to talk about is the effect of pressure on this system. So when we have an increase in pressure, we have to remember Boyle's law from last year's gas laws. These are all gases, and when we have an increase in pressure, we have a decrease in volume. They are inversely proportional. Okay, so the system, if we increase in pressure, we want to shift to the side where we alleviate pressure. So that means that we want to have fewer amounts of collisions happening and fewer number of moles of gas. So remember, pressure only affects gases. So in this case, when I look towards the left, I have 4 moles of gas, and on the right, I have 2 moles of gas. So if I'm increasing pressure, I want to shift to the side where I have fewer moles. That means I'll get fewer collisions, and therefore the pressure will come back down. So increasing pressure, the system wants to shift to alleviate that pressure. You shift to the side with the fewer moles. So in this particular case, I am going to shift towards the right. That means I'm going to increase the amount of ammonia, decreasing the pressure by decreasing the amount of N2 and H2 in the system, okay? And again, pressure has no effect on KEQ either. Decreasing the pressure is the same thing as increasing the volume. If you increase the volume, you have more space for those particles to be colliding. And so a decrease in pressure means we want to shift the system towards making more pressure. And pressure is directly related to the number of collisions. So we want to create more moles. So in this particular case, we want to shift towards the left because I will then create more collisions, which will bring the pressure back up. So I'm going to shift left in this particular case, increasing the concentration of N2 and increasing the concentration of H2, thereby decreasing the concentration of ammonia. Okay, so there is an example of Le Chatelier's principle and how various stresses affect that system at equilibrium and how KEQ is affected by temperature. I wanted to also show you something else in terms of graphical analysis for Le Chatelier. You'll also see this in an upcoming slide as well. So here we have a reaction, and again, they give the enthalpy value of -58. So that would be like putting energy towards the right because that's an exothermic equation. So what happens here is you have a system that is at equilibrium. We see that it's plateaued, and then all of a sudden you see this spike in the graph. And what that tells you is there was a disturbance at that particular point in time. Whenever you see a vast spike, that means that there was a change in concentration. So in this case, what happened was there was an increase of NO2. So they increase that concentration. The system then says, oh no, it has to respond to bring that back down. So the way it does that is to shift towards the right to make more N2O4. So you see that this will start to go up. And over time, after that initial spike, this NO2 will then start to go down. Notice that it's not down to where it was before, but we've just reestablished a new equilibrium where the ratios keep that KEQ value in check. So again, same sort of thing if you were to remove some of that NO2. So let's say that this is now dropping, okay? That gets removed from the system. The system says, oh no, we have to shift to make more of it. So what happens is if that drops, then eventually that concentration will go back up because we are making more and that concentration will go down, okay? And same with the addition of N2O4. Now let's take a look at what happens when we have a change in temperature. You notice that there is no spike, it's gradual. So let's just say that we have a decrease in temperature. So we drop that energy value, which happens to be found on the right. So that means that we need to shift to bring that energy value back up. So we would shift towards the right, and we want to bring the N2O4 back up as well because we're shifting towards the right. And again, graphically, that's what's happening. So that goes up, and this one will be going down because we're shifting towards the right. So it's gradual for both. Now, another thing that I should bring up is how does a catalyst affect the rate of these equilibrium systems? And what happens is a catalyst, because it will lower the activation energy of both the forward and the reverse reaction proportionally, the catalyst will have the same effect. It will just get you to equilibrium faster, but it doesn't cause a shift in one direction or another.